detect the radiation by the what do you call this?
Okay. Well, what kind of radiation detector you are using if you use it in your work or something?
Yeah, this is what is called this. I actually forget the name.
Okay. Anyways, the radiation detector is using to detect or to sense the radiation present. Okay. So first of all, ionization radiation is not detectable by human sense. So that's why we need a specific and a special instrument or material to sense or detect the radiation. Okay, so by our human sense, we cannot sense the radiation. Okay, so that maybe will be exposed for radiation without feeling this radiation. So for radiation protection, we need instrument or material, okay, to protect ourselves and to detect any radiation around, okay. So the radiation, you cannot smell radiation, or you cannot hear it or taste it, okay. So even you cannot feel it, okay. To address this problem, special, as I mentioned, the special instrument material are needed to detect and identify ionization radiation. Okay, sometimes we need to identify, to know the radiation type. Okay, or just to know is there any radiation or not. So every application of, radiation applications, okay, it depends on how radiation interacts with the material, okay? So interaction of radiation with the matter can cause ionization, excitation of the medium, whether gas or solid or liquid. Also changes the chemical medium, okay? For example, if the material upon exposed to radiation, the color can be changed, okay? So based on this two interaction, we can sense and we can detect the radiation. So the detector system use one of the previous radiation medium interaction to detect the radiation, okay? Why do we need radiation detection, okay? Or what kind of application for radiation detection? Okay, so we are using radiation detection or radiation detector to protect ourselves, okay, or to protect the environment from the radiation. Okay, radiation has actually advantage over his disadvantages. Okay, but even we need to protect ourselves from even low dose. Okay. Radiation, radiation detection or radiation detector, we use it for survey work areas, okay, to try to protect ourselves, as I told you, and to keep the dose around as low as possible, okay, within the normal limit. Also, we need radiation detection to measure exposure, measure patient in the medical applications, for measure patient or worker doses. We use it also for diagnostic, counting, imaging, and for industrial, which you care about it, industrial radiographic or NDT application. NDT application means non-destructive testing. Radiation detector, we will, in this lecture, okay, we will see something about the detector properties, how detector work, and different types of radiation detectors. And we will see the detector application. These properties or features, we care about it for radiation detector, okay? So we have to focus on some factors that affect on the radiation measurements, okay? Radiation doses. First of all, detector sensitivity, okay? We have to know the sensitivity of our detector, okay? Detector efficiency, energy resolution of detector, time resolution of detector, or its pulse resolving time, okay? Operating voltage. So anyone can tell me what is the detector sensitivity? Is it new for you?
It's like if the radiation leaking or like this. You give me a signal.
Sorry, can you say it again?
If it is there is the presence of the radiation, and sometimes some instrument cannot detect if the ability of the detection of radiation is the sensitivity of the detector.
Okay.
I think it's how fast the detector can detect the radiation.
Maybe this kind of time resolution. Yeah, the sensitivity of solid state, as you can see, state detector is about 10,000 times higher than that of gas field detector because of energy required. This is what I mean by sensitivity. Energy required to produce an ion pair is very low, and we will know in the next slides what is what is ion pair, okay, and what energy required to create this kind of ion pairs, okay, is very low. If energy consumed by or deposited to the detector medium as low as possible, that means the radiation detector is sensitive, okay. Higher material density, 3 orders more than compared to gases. This is the solid state detectors, so it's more sensitive than gas detector. Yeah, so if you can understand the sensitivity of detector from this kind of 2 things, energy required to produce an ion pair is very low compared to gas detectors. Higher material density also will help to make the detector more sensitive. We will see the difference between this kind of detectors. So also the sensitivity is also related to the what type of radiation detector is able to detect. Okay, if detector able to detect low energy alpha or something, so we can say this detector is high sensitive. Okay, for example, the salt scintillator has low sensitivity to detect alpha particle because of alpha particle cannot, okay, low sensitivity. The solid scintillator has low sensitivity because for alpha particle, because alpha particle cannot penetrate the detector case. Okay, so scintillator, or specifically solid scintillator, cannot detect alpha particles. Okay, we need more sensitive detector to detect this kind of radiation type. Sometimes the efficiency and sensitivity, it's almost the same idioms, okay? And in some papers or some textbook, you will find there's something different, okay? Detector efficiency, the detector efficiency is defined by the fraction of the event measured, okay, by the detector with respect to the number of event radiation or event radiation source is emitted, okay. So this is the equation, number of measured by number of event or interaction, okay, that recorded by detectors compared to the number of events emitted by source. For example, gamma. For example, gamma. If the cesium emit, for example, 1,000 gamma, okay, and the detector just measure 500, so we can say that detector efficiency is 50%. Is that clear? The efficiency of the proportional detector, and also we will know what is the proportional counter or detector. So if the efficiency of proportional detector to detect gamma is low, so is normal, not used for gamma counting. However, it is considered as good as energy measuring detectors. Okay, so we can now see how some detectors is not efficient enough, but it can be useful in different applications. Okay? We use detector to measure the radiation, to count the radiation, to identify what kind of radiation. Okay, so some detectors is efficient for counting, but is not efficient for identification of the radiation type. Okay, energy resolution. Anyone can tell me about this? Detector energy resolution. Don't read it. Anyways, detector energy resolution can be defined as its ability to distinguish between two close energy. Okay. Now the radiation detector is hit by, for example, gamma. Gamma with a different for cesium or cobalt-60 has two different energy. If the detector able to distinguish between two close, for example, 117 and 1.33 in this example is cobalt-60. So if the detector can distinguish between two energies and produce two peaks, each peaks for each energy, so the detector has good energy resolution. And energy resolution is very, very important property for detector when the detector is used to identify the type of radiation. So in radiation protection practice, we normally use detector to do survey, to just to detect if there is radiation or not, or to try to find the lost isotopes. Okay, for example, the cobalt or cesium if lost. So how to know that isotopes is lost? Is this the way to identify the radiation isotopes or radioactive material using detector with good energy resolution to identify the isotopes. This is just more explanation to understand what is energy resolution. This is just part of a spectrum that radiation detector measure. So we can define the energy resolution for this detector by difference between two channels. Okay, two channels mean two different energy. Okay, divided by the let's make it easy. Okay, if this peak, okay, the full width at half maximum, if we could measure it, actually it's 1 and 2 is almost the same. Okay, it's the same, but I will start with the number 2. It will be easy. If you measure the width of the peak at the midi and the half of this peak, if you measure it, or sometimes it's kind of standard deviation, okay, and divided by the mean of this value under this peak, you can find, actually you can work out the energy resolution of this detector. And this is just two examples between just to compare the good resolution detector and poor resolution detector. And in the left side, the good resolution detector, we can see the full width at half maximum. The width of the peak is smaller than the poor resolution, the peak produced by poor resolution detector. So when the pulse, we call it pulse or peak of this radiation interaction event, if white, that means the resolution of detector is really poor. So the figure and right tell us, it tells us if the detector has poor resolution, so you will lose some information, some useful information. You can see the dashed peak, it's wide. Okay, so we lost the information about 2 energy under this peak. But with a good resolution detector, you can detect 2 peaks and you can identify this kind of radiation. Time resolution, someone mentioned to that. It's how high counting rate will be measured by detector with the smallest error, or sometimes without error. Okay, so if the time resolution is good for this detector, or the detector has good time resolution, so you will count in high level radiation easier and with the accurate result. Also, we can define the time resolution by how accurate and precise can one measure the time of arrival of particle at the detector. Okay, this is what we mean by time resolution. Is what we just talk about, just a simple introduction, and you will understand. I know some of you maybe couldn't understand what kind of what is this. I mean the properties of detector, but when you see the next slide, maybe you will understand some of that idioms what you just talked about. How detector work? Okay, as we see the first slide. Okay, we talk about interaction of material or radiation with the material. Two mechanisms: interaction through ionization or excitation, or chemical change in this material. So this is the 2 main interactions that detector is based on in its work. Any material that exhibit measurable radiation related change can be used as a detector for ionization radiation. So if the color change, so we can calibrate this kind of things just to use it as indicator for the radiation dose. Or chemical changes, or emission of visible light, or electrical charge. This is just summary. Okay, you can see it later. This is just summary what I talked about. Detector operation mode. The detector can be operated in 2 main modes: current mode or pulse mode. Current mode measure the current produced by the detector. This is if we sense the electrical charge. We measure high level of radiation, and 2 main detector use this current mode for it is the dosimeter and radiation survey, or surveymeter. Pulse mode used with the detector to record output of each individual event, amplitude and timing at low level of radiation. For example, detector is operated by this mode when user looking for identifying the radiation isotopes. So the detector will produce peaks at different So pulse mode means the detector will produce a spectrum with the different peaks. Each peak has specific energy. It will be used to or related to specific isotopes. So we have 2 different modes for operating radiation detector. The detector can be used for as a counter, means count the number of interaction, and this can operate in pulse mode, or as a spectrometer, number and energy of interaction. This is the detector will be designed to measure the number and this will be operate in pulse mode, or can be detector can be used as a dosimeter, just measure the net of deposited energy in the medium of the detector. And in this case, we will operate the detector in what we call a current mode. Radiation imaging, using radiation detector in imaging. So we can, for CT, for example, CT scan, we can use it or operate the detector or measure the signal by current mode, or for nuclear medicine, measure pulse mode. And this applies also to the industrial application. For if you wanted to, for radiographic, for example, we measure it or we operate the detector in pulse mode. Different type of radiation detectors. Detector actually can be classified for its material, for the material used to build the detector. For example, in this case, gaseous detector. This is kind of classification for different detector, gaseous detector, because of the main or the active medium is gas. Solid state or semiconductor detector. Scintillator. Also scintillator, we can call it solid state, but scintillator can be liquid or solid. Okay, there's two different also, organic and inorganic. Radiographic film and thermoluminescence detector. This is the main or the famous detector types. We will start with the gas radiation detector. The gas detector, because the main medium in this detector is gas. Okay, it's kind of tube filled with the gas. This gas interacts, or the when this gas hit by radiation, it will produce ion pair. It will ionize the gas and produce ion pair. If you can see the here, this is what we call ion pair. Okay, it's electron and ion, electron and ion, as a result of ionization of gas by radiation, by ionizing radiation. In this graph, you can see it's the gas detector can be in different forms. Okay, but the basic is the same basic. Okay, it's composite of anode, which is positive charge electrode, and cathode. Okay, and the gas is between of them. When the radiation interact with the gas, it will produce ionize the gas and produce ion pair, and because of the electric field applied on the gas, so the cathode will attract the positive ion, and the anode, which is positive electrode, will attract the electron. Okay, so we can measure this current or charge. It depends on the electronic you use. So you can relate it later. You can relate the number of a charge you measure it or current to the absorbed dose. Do you prefer to take 10 minutes for prayer? Hello, can you hear me?
Yes, yes.
Yeah, you wanted to take a break for prayer, or you wanted to continue?
I mean, break is fine, 10 minutes, then we can go back.
Okay. Then we will take 10 minutes, okay? We just started, but because of prayer time, if you want to pray, and we will be back. السلام عليكم. Hello. Should we start it?
Yes, teacher.
Okay, good. So we stopped we started just gaseous radiation detector, and we said this kind of detector is based on the gas, okay, to detect radiation. It's instrument or tube or whatever. It comes with the different forms, but the same mechanism. It filled with the gas, different gases, different for different application. The gas upon radiation exposure will produce what we call it ion pair, or gas will be ionized, and because of the gas is between two electrodes, when apply electrical fields, the charge just released by radiation will attract to each anode, and then we can measure the current as a result of that, okay? And we can just link between the result of, or the current or charge produced at this gas to the radiation dose. Is that clear? So gases detector actually also by itself, it classified two different detectors. We call it ionization chamber or ion chamber, proportional counter, Geiger-Miller counter, all of them gaseous detector, okay? And the same mechanism. The only difference, anyone can tell me what is different? All gaseous detector, but why we classify this detector by this name? The difference between each type, actually, the voltage or the electrical field applied between two electrodes. Okay, and we will see it one by one. First of all, ionization chamber or ion chamber. Ionization chamber is gas detector, but when applied electrical field around this value, it's 10⁴ voltage by meter, which is electrical field unit, is used to collect all the ionization produced by the incident radiation in the gas volume. I don't know if you can see my mouse. Wait. So in this region, the light blue region, it's called ionization chamber, and because of we applied a specific value of electrical field in this area, but before this area, okay, or this region, we cannot use this for radiation detector because of the electrical field applied in this region is not enough to collect all ionization produced by radiation, and it will recombine again, so it will not reflect the real dose deposited by radiation. So that's why in this region, before the ionization chamber, we don't use this area or this voltage region, or we don't operate the detector at this value of electrical field. So we started from here. This is the ionization chamber until a specific value. After that, we will enter different region or different radiation detector. We will talk about it later. So in this ionization chamber, every ionization or ion pair produced by ionization by radiation, ionizing radiation, it will be collected. Okay, and it will be independent of applied voltage in this area. And this is clear from this plateau. Okay, when you change the voltage in this area, it will not be make difference. Okay, so we call it saturation area as well. Okay, you can see the name saturated ionization chamber. Saturated ionization chamber because whenever you change the voltage in this area, it will not make any difference because all ion pair produced by ionizing radiation collected completely. So in this area, no amplification means only the ion pair produced by radiation, it will be collected, no more than that. And we will understand this point actually when we discuss the proportional counter. So ionization, to be just remember, ionization chamber, no amplification, no gas amplification means no more than just what radiation produced. No dead time, high accuracy, stable. This is the ionization chamber. It's high accuracy, so we use ionization chamber to calibrate other detector. It's high accurate and stable. Stable because of when you change the radiation, or I mean the voltage, it will not make difference. It will be stable for certain value of voltage. Signal reflects formed charge. The pulse actually produced by this detector is very weak because no more amplification, because only the ion pair produced by ionization, it will be collected. So usually actually the ionization by radiation, I mean, the ion pair, it's very low, okay? So usually you need to connect the detector by electronics to amplify the signal, okay, out of detector. So it's relatively low sensitive for gamma efficiency. I mean, gamma efficiency of this ionization chamber is low. Anyone can tell me why the ionization chamber is relatively low sensitive? Why ionization chamber is low efficiency for gamma? Okay, I will leave it for you. So anyone want to answer later, no problem. And I will try to tell you the reason at the end of this lecture. Sometimes we need to build up caps, sometimes needed to enhance detector efficiency when measuring high energy photon radiation. And actually, this is kind of part of the answer. Survey meter for detect beta. We can use ionization chamber to detect beta or alpha, but we need to use thin end window because, you know, alpha, it can be stopped by paper. So we need thin end window to allow more penetrating particle to be detected. And the ionization chamber also used for because accurate and stable. Proportional counter, which is the region just followed by or just after ionization chamber region, because we increase the electrical field applied between two electrodes. It's around 10 or around 1 million volt per meter, which was enough to cause what we call gas amplification, and we will understand what gas amplification. When applied voltage is higher and the electrical field is getting stronger, what will happen inside the gas? Okay. This is the region of ionization chamber. Primary ions just hit gas, produce electron, ion and electron. So in ionization chamber region, we just measure this. Okay. So that's why we say the ionization chamber, the signal from the ionization chamber is very low because only this produced by radiation will be measured. But when we applied higher voltage, the ions, produced ions and electron will be accelerated, means will gain more energy and it will do another job. What is that job? It's ionization, more ionization for the gas, okay? So we have two steps of our two phases of ionization by primary ions and by accelerated ions as a result of applied high voltage. So we'll produce secondary ions. Here, what we mean by gas amplification. So let's tell you again, when applied voltage is higher and the electric field getting stronger, the ions or ion pair can be accelerated to each electrode, and in their way will gain sufficient energy able to initiate further ionization. So the ionization from primary ions and by accelerated produced ion, and it will produce more secondary ions, and we will measure it as what we did actually with the ionization chamber. The proportional counter has some properties which is actually useful in some application. It is higher sensitive detectors compared to ionization detector. Gas amplification, it's about 1,000 to 10,000 compared to the ionization chamber. Ionization chamber, no amplification. It can be used for particle and low energy photons because small or low energy can produce this kind of signal, which is easy to be detected. But if we use low energy radiation with the ionization chamber, it will not be easy to detect. So we use ionization chamber for high energy radiation or photons, and the proportional counter, because or thanks to the gas amplification, we can use it to sense the low energy, so it's more sensitive. Can be used for neutron detection, spectroscopy, and used as a spectroscopy as it can distinguish between alpha and beta. Back to the Ionization chamber and proportional counter, if you can see two lines in green and light. Okay, so red and green, it's different energy. So ionization chamber can distinguish between two energies, two different type of radiation, and also the proportional counter can also distinguish between different types of radiation. When we increase the voltage, the applied voltage further, what will happen? Okay. Before that, let's say, I forget this slide. The size of the produced pulse in a proportional counter depends on two factors. If you remember, we told you, I told you that the pulse produced from the ionization chamber is weak, okay, because there is no gas amplification. But here it's high because of gas amplification. And actually, the height of pulse in a proportional counter will depend on operating voltage, but you can see the difference between the pulse from the ionization chamber and the proportional counter and how operating voltage affected this pulse height. Energy deposited in detector gas. The greater the energy deposited, the larger the pulse. The process of the charge amplification greatly improved the signal to noise ratio of the detector and reduced the subsequent electronic amplification required. For ionization chamber, I repeated many times, but for ionization chamber, we need more electronics because of the signal produced from the ionization chamber. It's very low, so we need to make it bigger by amplification, and we use specific electronic for that. But in proportional counter, sometimes we don't need it, and this will affect the cost of the detector. If you don't need more electronics, so it will be cheaper than ionization chamber. And this will be more clear in Geiger-Miller, because Geiger-Miller is very cheap detector. And because also for this, we can attribute it to the same reason, because we increase the high voltage, the applied voltage more than 1 million volt by meter. So we enter to different region, which is Geiger-Miller region. Here you can see the two lines for detection, or the two different types of radiation. Now it becomes one line. So it becomes one line. Okay, so energy here, you cannot, the detector in this region will not give you more information about energy. So will not tell you this is alpha or beta or gamma or whatever. That's why we use it just for surveymeter. We don't use it as a spectrometer. We don't use it for identification, different type of radiation. So the gas amplification in this case, it's more double than proportional counter. So the signal produced from a Geiger-Miller is very, very high. So we don't need electronics. This effect on its price, okay, it's very, very cheap compared to other detectors. Gas amplification is about in Geiger-Miller detector. It's 10⁸. Output pulse size is independent of the initial energy. Now you cannot sense the different energy, cannot distinguish between two different energy, and long dead time, okay, and it can be used in low level of radiation, higher sensitivity. So you can now link between the gas amplification or applied voltage and sensitivity. The sensitivity increase as the applied voltage is increased. Simple. You don't need that complex electronic to measure the signal or to make it bigger, and so it will cost less compared to other. Geiger counter used as a surveymeter for to detect the contamination, or and also use very low level radiation because of its high sensitive. And at the high level radiation, that this detector, because of also applied voltage is high, it will paralyze the collecting the ion pair produced by radiation. So it will give 0 in high level radiation. Another detector, this is, we finished now with the gas detectors, and with three main different types. Now we will discuss other detector. We call it scintillation detector or scintillator detector. It depends on the scintillator is using a different material or specific material that produce light when exposed to ionizing radiation. It can produce different wavelength light, as you can see from the image on the right side: red color, green, blue, ultraviolet, or visible light. Ionizing radiation interact with the scintillator, which produce pulse of light. And the light will produced by this material, it will be converted to electrical signal, and we will measure it as we just did with the ionization gas detector. So this is the setup of scintillator detector. This is the scintillator crystal or scintillator material. It can be solid, it can be liquid. It's different form of scintillator, but the mechanism is the same. When incident particle or photons hit the crystal, will produce light, because this radiation excites the atom, this material, and it will produce light. This light, it will be converted through a specific material here. We call it photocathode, to produce electron. And this electron, it will pass through this area. We call it photomultiplier, PMT. PMT job is just to amplify the signal, to make it bigger, because the detector, the signal produced by any detector is very, very low. So that's why we need specific electronic to make it easier to detect the signal and easy to process it later, to use it in any different application. Can be used for imaging, can be used for counting, can be used for just use it as a spectrum to identify the different radiation. The number of counts is dependent on the activity. If the isotopes or other sources high activity, so the number of counts it will be high. The energy of the electron and consequently the associated current is proportional to the incident energy. If you deposited more energy in this crystal, it will produce more electrons, more photons, and it will be converted to more electrons. By analyzing the energy and corresponding number of counts, the nuclei and activity may be determined if we use it as a spectrometer. This is just kind of definition. Later, you will maybe use it or to understand some mechanism of radiation detectors, or luminescence, emission of photons, visible or UV or X-ray, whatever, after absorption of energy. So if the material or you deposit the energy by light, it will call photoluminescence. If you will produce this luminescence because of material exposed to heat, so it will call thermoluminescence. Scintillation, emission of photon following the excitation of atoms by radiation, gamma or alpha particle or beta particle or neutron. Fluorescence, emission of light by substance that absorbed light or another electromagnetic radiation of a different wavelengths. In most cases, emitted light has a longer wavelength. And phosphorescence is just the same fluorescence, but it is just emitted directly after the absorption of light. Classification, as we classified the gases detector, also we can classify the scintillator. It can be organic or inorganic, can be solid, can be liquid. So there's different classification for the scintillator. So the main classification is organic and non-organic. Organic, like plastic detector, has low Z. It cannot be used actually good for high stopping detector for high energy. It can be used just for gamma for low energy, or can be used for a neutron because of low Z. The decay time in nanosecond, relatively inexpensive. Okay, it can be used for as a counter or tracking. Inorganic, like sodium iodide. This is one famous detector, sodium iodide. I don't know if you heard about it or not, but it has really high yield of photons when, for example, 1 mega electron volt per from gamma, or can produce 40,000 photons. It has high atomic number or density, so it can be used for high energy. And actually the sodium iodide is used mostly for gamma. It's expensive. Application can be used for medical imaging or imaging in general, high stopping power application. Scintillation detector, there's something we need to, some feature we needed to be in use scintillation detector efficiently. The scintillation detector should, or the material of scintillation scintillator should be should have high conversion efficiency. Decay time of excited state should be short to avoid lost information from the coming radiation hit the crystal. So the light produced in the crystal should be quickly, should be fast. That's what we mean by decay type. Material transparent to its own emission, not to attenuate the produced light. Should be mechanically, should be rigid and unaffected by moisture and inexpensive, like a plastic scintillator. It can be used usefully actually in different applications, and it's inexpensive and can be produced with a large footprint. Examples: sodium iodide, which is anorganic material or anorganic scintillator, mostly used for gamma detection because of high atomic number, high Z. Plastic scintillator, solution of fluorescent compound included in transparent plastic material. This is how to make plastic scintillator, mostly used for beta particle. Zinc sulfide, used for detection of alpha particles. This is just also summary for different material used for different scintillator, organic or non-organic, and different application. So anyone interested can just read this table. Another detector types. Let me ask you questions. Did you face any problem with this? I mean, scintillator detector or gaseous? Do you have a questions? Can you hear me?
So in the test, if we go to the radiation safety officer test, what kind of questions will be asked about the detectors and everything, like define or what type of detector is this? What type of questions will face?
Maybe it will be asked about I don't know actually about the question. Okay, and in this course, I think you will have chance to solve some problems. Okay, but maybe they will ask you about detection, for example, different type of radiation. And we will see, for example, neutron. Do you know how to detect the neutron? Neutron, it's not charged particle. And what we explain in ionization chamber and the scintillator and not scintillator, ionization chamber, the radiation, it will cause ionization, okay? But neutron, it will not be a charged particle, it's a natural particle. So how can we use it to produce or to detect neutron, for example, or different type, or what kind of detector is useful in this specific case? So alpha, beta, gamma. So I expect this kind of question, but I don't have actually, and you will have chance to have some question about also in detectors. So anyone in this group can help? What kind of question? They will ask about type of detectors used for a specific application.
Yeah, they are mainly
Efficiency calculation.
Yeah, efficiency calculation, and then the for the laboratory purposes, which one, this iodide, that one is why it is using in the laboratory purpose, something like this. They're making the question.
Yeah, yeah.
And
So
Geiger-Müller, this detector, why it is, I think it is mostly is usable. That's why they're asking some the question, and they're asking the mechanism, say how the detector functioning. This I detect this radiation is focused on the gas chamber, and then it's convert to electrical current, and then detect like this mechanism. They are sometime making the question.
okay, good. I hope that was useful.
Yes, yes, thank you.
But don't worry. I think there's a session just dedicated for this kind of question. Semiconductor detector, and sometimes we call it solid state detectors. But solid state, it's kind of large idioms or large topic. It will include us also the scintillator. So in this radiation detector, a semiconductor material such as silicon or germanium crystal is the active detection medium. Just like the gas, we use gas as the active medium, okay, for a gas detector. In this, we replace the gas detector, but using the solid state detectors, solid state material or semiconductor material, silicon germanium. It requires low radiation energy to produce an ion pair, electron holes in this case, which is about 3 to 5 electron volt. I think this is maybe you will be asked about it, okay? The gas detector, do you know the energy required to produce ion pair? It's around 34, okay? From 33 to 35 electron volt. But the semiconductor only 3 to 5 electron volt. Can you imagine the difference between of them? Because of silicon and germanium, it's high, they have high density, okay, compared to gas. So because of density, and when we just talk about sensitivity, we just said the required energy is low. So here, the required energy to just produce ionization, it's very low, 3 to 5. While in gas detector, we need 35 electron volt to produce the ion pair. Just to see the difference between them. Here, how it semiconductor works. So when radiation, the red arrow, hit the detectors. Actually, the detector is composite of two types of semiconductor, N types, which is the most charged particle or carrier charge is negative, and the positive or B type. Here you can see it. The most charged carrier here is positive, or we call it hole. It's not exactly hole, but lack of electrons in this part. So between two parts or two layers, N type and B type, there's depletion because this material reverse voltage is applied here. Okay, so it will create different region between the B type and N type. This area, call it depleted region. Okay, there is no dominant charge here, no positive, no negative. So when this is the active volume or the sensitive area of the detector or semiconductor. So when the detector hit by radiation, it will create the ion pair in the same manner to the gas detector mechanism. As this charge produce and there's applied voltage, it will collect the charge produced here and will produce signal, electrical signal. So electrical signal, it links to the deposit energy in this area. This is how it works. The sensitivity of this detector is about 10 or 100 times higher than that of gas field detector. Average energy required to produce ion pair, and we talked about it, actually is very low. Material density is typically 3 orders more than compared to the gases in general. The high sensitivity of semiconductor helps to produce this kind of detector in a small footprint. So the semiconductor is very, very small. Okay, this is the one of advantage of using high density material to manufacture detector. For high energy electron and gamma, semiconductor detector are much smaller than gaseous detector, also because of its density can stop the radiation. If you remember, we told about ionization chamber cannot be used actually in gamma efficiently. It can measure gamma, but it's not measure it efficiently. And I asked this question, but because of gamma, it will pass through the gas without enough ionization. Okay, because of low density of chamber. Okay, so the semiconductor is more useful in this case than just gas detector. Energy resolution can be improved by increasing number of charged carrier. Here's some advantage and disadvantage of silicon, for example, as one of the semiconductor. It's compact, excellent energy resolution, high density. If you compare it to the gas detector, detection system can be produced in a small footprint. One of disadvantages is susceptible to radiation damage. It can be damaged when used many times for radiation, especially for particles. Also need to be cooled. Need a cooling system for that, because if you remember, or anyone study about semiconductor, there is something what we call it dark current. Dark current means it's kind of dose, okay? There is current, and we need to stop any current as long as the semiconductor is not exposed to radiation. So in normal temperature, the silicon, it can produce current. This will make it difficult to use it as a detector actually. So we need to cool it to using cooling system for that. As alternative material for silicon, germanium, because it can be used efficiently to overcome some disadvantage of silicon. gallium arsenide, silicon carbide. Also, this is kind of a new detector. Germanium used instead of silicon for gamma detection. If you can see that its density higher than silicon, it's kind of double. Energy required to produce electron hole is about 2.9 electron volt, and silicon 3.6 electron volt. So this is some of main advantages of germanium. It has disadvantage or drawbacks: low forbidden gap, susceptible to thermal excitation. Forbidden gap, it's the gap between the conduction band and valence band. Okay, so if the forbidden gap, okay, forbidden means electron cannot be there. Okay, so electron can be in valence band or conduction band. If the forbidden gap is small, so it's easy for the electron to jump to valence band, so to conduction band, so can produce also dark current and at room temperature or at low or thermal, or we call it thermal excitation. So need also cooling. I just mentioned too how to detect some types of charge radiation, okay? And all radiation photons, alpha particle, beta particle, can directly ionize the active medium, wherever it's gas or semiconductor or scintillator. But neutron is not charged particle, okay? So cannot directly ionize the radiation, cannot be directly ionize the gas or semiconductor or scintillator. So it's need to be converted to detectable radiation, for example, charged particle. So it's kind of two steps to detect neutrons. Every type of neutron detector must provide with the converted medium to convert the neutron from, we have two different type of neutron, fast neutron and thermal neutron, or a slow neutron or low energy neutron. So we need to convert the neutron to alpha particle, for example, or to gamma, and then we can detect gamma and detect alpha particle. Okay. Scintillation, gaseous, and semiconductor can be used for all detector can be used to detect neutron, but we need specific modification or some modification just to convert neutrons to different detectable radiation. Two main interaction for neutron: scattering and nuclear reaction. Scattering, recoiling, when like billiard balls, recoiling nucleus. This is the kind of interaction between the neutron and neutron of or nucleus. Okay, and this will be dominant for the light elements such as hydrogen. So the scattering happened with low atomic number material. And what will happen? It's kind of recoiling nucleus ionized surrounding materials. A nuclear reaction projects the neutron. It will cause or produce excited atom or nucleus, and then back to the ground state. The nucleus will produce alpha or fission fragments or gamma or proton. So at this case, we can detect gamma or alpha or proton. Ionization chamber, if we, for example, use it to detect neutron, so we need to have gas used. In this case, is boron, BF3. Boron, when hit by neutron, it will produce alpha particle, and lithium. Okay, so in this case, we can sense or we can detect alpha. So we didn't detect neutron directly, but indirectly. Okay, so neutron hit boron and then produce alpha, and the ionization chamber just detect alpha. Alpha will ionize the gas later. So boron telluride, it used in ionization chamber to convert neutron to detectable alpha particle. Also, we can use for proportional counter helium. When we hit helium, it's kind of isotopes of one of isotopes of helium isotopes. When hit by neutron, it will produce hit by neutron, it will produce proton. So we can detect proton as a charged particle. Lithium-based scintillator. We cover scintillator by lithium. So when a neutron hits lithium, it will produce helium and alpha particle. So the later scintillator can detect or can sense the alpha particle and detect the neutron. Now we finish radiation detectors, and we will just now take some slides. We'll discuss some slides about radiation dosimeter, which is detectors. But to prepare you for the next lecture, so dosimeter is a detector that measures directly or indirectly the deposit energy doses by ionizing radiation such as exposure, absorbed dose, equivalent, and karma. So in this case, we just care about deposited energy. We don't care about the type of radiation. Okay. We don't use the radiation as a counter or as a spectrometer or not. We use it just as a dosimeter. So the dosimeter is a specific detectors, which is detector like ionization chamber or scintillator or whatever, but it's designed just to measure the deposited energy. So different type of or different units can be measured: exposure, absorbed dose, equivalent, effective dose, and karma. Here are some definition. Exposure is measure of the ionization of air induced by X-ray or gamma rays. The SI unit is Roentgen, and Roentgen, one Roentgen equal to 2.58 times 10⁻⁴ coulomb per kilogram. So if the air or dry air hit by X-ray or gamma, it will produce this number of charge in 1 kilogram. Absorbed dose is the deposited energy per unit of mass. Okay. And the SI unit is gray and equal to joule. It's the energy unit by kilogram. Deposited energy, joule per mass or kilogram. And there is a relationship between exposure and absorbed dose. Absorbed dose equal to the exposure. Okay, it's the exposure or the produced charge in this mass, okay, of air or tissue, for example, times the average ionization energy needed to produce the charge. Okay, if you just do this kind of calculation, you can just see unit coulomb per kilogram times joule per kilogram per coulomb. So coulomb were removed by with the coulomb, so it will joule per kilogram, which is the dose. Equivalent dose is just absorbed dose times the weighting factor of radiation, okay, of different type of radiation. The absorbed dose will not give you that information about if you were exposed to. Let me ask it as a question, okay, to be more on this to be more clear, okay. If 1 gray from alpha particles and 1 gray from X-ray, do you think the absorbed dose is the same? the observed dose. It's just 1 gray from each other. If you expose to alpha, it's not alpha, let's say neutron, okay, because alpha is not that harmful outside of body. But if you expose to 1 gray of neutron and 1 gray of X-ray, do you think it will be the same? As absorbed dose?
No, but does it also consider the time of exposure?
No, forget the time now. It's because of the exposure rate or dose rate is different things. We will see it. But I mean, as a dose, what I want to say, it's just we use weighting factor for radiation because X-ray.
It will not same because there is a.
It has weighting factor.
Yeah. Say the for
X-ray.
gamma particle.
You say the same?
The alpha 20. Something like that, they have the factor, so we have to multiply it by a factor, so it will be not the same, it will be different.
Yes, good. It will not be the same if the absorbed dose is the same, but if equivalent dose, that's why we need equivalent dose, okay, to take into account the type of radiation, because the neutron or alpha, it will be 20 times higher than just the ionization caused by X-ray. Okay, so that's why we need equivalent dose to take into account the different type of radiation. So the dose, observed dose, with times the weighting factor of different radiation, it will produce new unit. We call it equivalent dose for different radiation. And the SI unit is Sievert. Effective dose also, we want to, because the body is not the same sensitivity to the radiation. For example, if you expose to X-ray, the whole body, okay, the eye has a specific sensitivity or has sensitivity different, and hand has a different sensitivity to the exposed. If your hand exposed to X-ray, I mean, for example, 1 millisievert, for example. The eye, your eye, if exposed to 1 millisievert, and your hand exposed to 1 millisievert, it will not be the same because the sensitivity of organ is different. Okay, so that's why also we need weighting factor for the tissue or the organ. So that's why we use weighting factor times the equivalent dose, and we produce another effective dose, and the effective dose is the useful the unit to estimate the biological effect. So effective dose, it's more accurate than observed dose. Of course, absorbed dose, it will give you indication, okay? But if you will care about the biological effect, you have to measure, or you have to calculate, work out the effective dose. Kerma is measure of the energy transferred from radiation to matter, and its acronym to kinetic energy released to matter. This unit is the same. Actually, the Kerma is almost the same to the absorbed dose. A useful dosimeter exhibits the following properties: high accuracy and reproducibility, precision. So if you use the dosimeter today and tomorrow, it should produce the same measurements. After 1 month, should produce the same measurements. If the measurements is different, so it cannot be used as a dosimeter. To keep the dosimeter at good conditions, so we need something, and we will discuss later the calibration of this instrument. So linearity of the measured signal against deposited energy. If you increase the deposited energy, so the signal measured by the dosimeter should be also the proportional to the deposited energy. Otherwise, this dosimeter will not be useful. A small dependence on of the signal on, I mean the measured signal from by dosimeter should be independent of or a small dependence. And dose rate, beam quality, and direction. The response curve for ionization chamber, it's kind of saturated or something. So when you measure different energy by ionization chamber, it will not be different. So the ionization chamber, it will produce almost accurate result. So that's why what we mean by independent of the beam quality or beam energy. So if you measure different energy by this dosimeter, should give you same energy, okay, for the dosimeter. For the absorbed dose, if you deposited energy, energy, or we call it dose produced from alpha or beta, should measure actually the same, or with a small dependence on this kind of dose rate, beam quality, direction, because we the dosimeter, it will affect by direction, of course, but what we are looking for to minimize the dependence of the dosimeter on the direction. Okay, if the dosimeter affects by direction from the source of radiation, affects much, so it will not be used as a useful dosimeter. This is just more definition if you wanted to know about what is accuracy and precision. Dosimeter can be classified as active and passive. Immediately, this is the active dosimeter. Immediately display dose value you just export to it. Passive doesn't display recorded dose directly, but need other devices or accessories to read a stored signal, like TLD, if you know TLD. Active dosimeter, like ionization chamber, semiconductor, it can give you directly the dose. Used in work with the environment with a high radiation level, radiation accident, additional awareness of unexpected exposure, area monitoring to give you any change in radiation level directly. So if you use TLD, for example, or passive detector, and something happened, accident, it will not sense this, and you will not know there's something happened or the radiation level changed. So you need active dosimeter that give you alarm directly when the exposure or radiation level change. Passive dosimeter, also useful, but in different application. One of the famous passive dosimeter is thermoluminescence TLD, optical stimulated luminescence OSLD, and this is new one. Film dosimeter radiographic, because will not give you direct measurements, need different devices or reader to reveal the dose. Its application, the application of passive dosimeter in certain cavity, phantom to measure skin or organ doses, wearable by individual who work in radiation environment, radiation worker, environmental monitoring. Then this, the first lecture, we finish it, and now we will start. Do you have any question about this lecture, or start directly to the personal dosimeter? Because I think this is a bit lighter than detector. So I will continue, but if you have question, you can ask anytime, no problem. So now we will discuss just a specific